Let's start with the basic architecture of an electric dipole. It consists of two charges of equal magnitude but opposite signs, a positive charge plus Q and a negative charge minus Q, separated by a specific distance, defined as 2a, centered around an origin point O. Now, suppose we want to measure the electric field at an arbitrary observation point in space, point P. We map its spatial relationship to the dipole's center using a radial distance, r, and an angle, theta, measured relative to the axis connecting our two charges. Our objective is to calculate the total scalar electric potential at this specific off-axis point. To find this total potential, we rely on the superposition principle. We calculate the scalar potential generated by the positive charge and add it to the scalar potential of the negative charge. Adding two scalars together is straightforward algebra. However, repeating discrete calculations for every point across a 360-degree radius is impractical. Mapping this field requires a single generalized mathematical model. The standard formula for electric potential requires the exact distance from each specific charge to our observation point. It is not enough to know the distance from the origin. We must map out the individual distances, r1 and r2, which forms an asymmetrical triangle. Expressing these diagonal distances purely through standard geometry yields mathematical expressions that are difficult to generalize across different points in space. Real-world physics offers a practical constraint. In an actual physical system, observation points are usually located at macroscopic distances, while the gap between atomic charges remains microscopic. This disparity in scale allows for a geometric assumption that simplifies the math. Constructing a generalized dipole equation depends on resolving this geometric bottleneck by approximating these individual diagonal distances at a macroscopic scale. This mathematical derivation diagram visualizes our geometric approximations. Here we see the charges, point P, and the radial vectors, r, r1, and r2. If P is sufficiently far away, vectors r, r1, and r2 are nearly parallel. By dropping a perpendicular line from the positive charge down to the central radial axis, we create a small right triangle. The base of this triangle is equal to a times the cosine of theta. This gives us our first geometric proof. The distance from the positive charge, r1, is roughly equal to the central radius r minus this small triangular base segment. We follow a parallel process for the negative charge. We extend the central radial axis backwards and drop a perpendicular line from minus q, creating another right triangle with an identical base segment of a times cosine theta. This establishes our second proof. The distance from the negative charge, r2, is roughly equal to the central radius r plus that triangular base. This entire geometric approximation is contingent on the observation distance r being large enough that those radial lines are effectively parallel, making the perpendicular drops valid. By replacing complex diagonal vectors with simple linear additions and subtractions, a two-dimensional geometric problem is reduced to basic scalar algebra. This algebraic progression shows the initial setup of our superposition equation. We factor out the constant, 1 over 4 pi epsilon 0, and substitute in our newly derived distance approximations for r1 and r2. To combine these two fractional terms into a single expression, we cross-multiply to find a common denominator. Multiplying the denominators together creates a difference of squares expression, r squared minus a squared cosine squared theta. When we combine the numerators during that cross-multiplication, the r terms cancel each other out, while the cosine terms add together, leaving us with q multiplied by 2a cosine theta. In physics, we define this specific algebraic grouping, the charge magnitude q multiplied by the total separation distance 2a, as the electric dipole moment, represented by the variable p. Substituting the electric dipole moment variable back into the numerator finalizes our intermediate formula. This intermediate algebraic equation successfully bundles the system's geometry and charge distribution into a single predictive expression, ready to be tested at its limits. To finalize this equation for field mapping, we apply a theoretical condition, scaling the observation distance r until the separation distance a between the charges becomes mathematically insignificant. Because a is small, squaring it reduces the a squared term to a negligible margin of error compared to the squared radius. As a result, we can eliminate the a squared term from the denominator entirely. We are left with the final equation for the potential of an electric dipole. V equals 1 over 4 pi epsilon 0 times p cosine theta over r squared. This final denominator reveals a significant property. Dipole potential decays at a rapid squared rate, 1 over r squared, dropping off much faster than the linear decay of a single isolated charge, solely due to the proximity of an opposite charge. To validate this generalized formula, we test its outputs against the extreme boundary cases along the dipole's axis to ensure it matches physical reality. For case 1, an angle of 0 degrees evaluates the cosine to positive 1, yielding maximum positive potential. In case 2, the opposite extreme at 180 degrees makes the cosine negative 1, yielding maximum negative potential. The generalized geometric formula predicts absolute scalar peaks along the axis without requiring any distinct, isolated geometric proofs. Our final test is case 3, placing the observation point anywhere perpendicular to the dipole axis on the equatorial plane. Substituting exactly 90 degrees into the cosine function yields a distinct result. A 0 multiplier instantly collapses the equation to 0. The physical significance of this result is clear. Any point on the equatorial plane is perfectly equidistant from both the positive and negative charges, causing exact and continuous scalar cancellation. Resolving the initial geometric bottleneck through approximation provides a single equation capable of predicting the entire spatial field of an electric dipole.